Hello everybody, today is December 9th, 2021, and you are joining us for the Hotfire of BZB. This will be our second attempt at a full Hotfire in this initial configuration. After some off-nominal data readings from our first Hotfire, it triggered an automatic abort, and today we're going to be doing another attempt. Here with me is Jack, and today we are going to be...
Alright, we don't really see any leaks. Do you want to get a leak rate?
As well as...
Yeah, we're going to go ahead and get a leak rate.
As well as adding any commentary we can
we're
over
going to
the...
close 203.
In addition
go ahead and
to
close
what we're doing.
MVN203. MVN203 is closed. Okay, we're starting our leak rate. Over.
So what we're doing right now is we're getting a leak rate for the overall system. And Jack, do you want to talk about what a leak rate is for a second and why it's important to give for a system?
So, in a liquid rocket such as ours, we have not only the rocket to worry about filling, but we also have a ground support system to support the rocket. So, our ground support system, BCLS, or the Black Cat launch system, has the ability to automatically fill our propellants into the vehicle to make sure our operators are safely behind cover. Now, in our fluid system, we have a bunch of fittings, fitting connections for all of our plumbing, so all of our fluids can make their way into the rocket. And on this fluid system, these fittings can be leak points. This can result in losses of pressure or fluid leaking out into the courtyard, which are undesirable outcomes for a hot fire.
And it kind of seems like we would have leak checked this entire thing beforehand. Do new leaks spring up between each operation?
If they are left for a certain amount of time and changes are made to the system, leaks can appear. So it is important after a prolonged period of time without any kind of test to perform leak rate checks again and adjust accordingly.
Got it. And so what we're doing right now overall is I believe the lock system, and this is very critical to make sure we aren't leaking because LOX is very nasty to work with. It can have
So we're still getting a leak rate of 4 to 5 psi a minute. We're going to go ahead and think it's the valve. I don't know if Courtyard has the same opinion as us. We're tempted to go ahead and accept. What are you thinking of there? Over. Yeah, we also think we're going to accept. We don't see any significant leaks. Over. Copy. I'm going to confirm with controller again, and I think we're going to accept.
So what goes into having an acceptable
Okay, it's
rate?
ground. We're going to go ahead and accept. So Courtyard, go ahead and open MVN203. MVN203 is open. Okay, retreat behind solid cover, and I will wait your confirmation.
So what goes into having an accepted leak rate versus a leak rate we reject on a certain system?
So it's kind of go at the pace of the system. We have a total acceptable leak rate for the system defined as this is what we think is safe for us to operate with. And when we leak check with nitrogen, we're able to do this in a safe manner and make sure that when we actually get to the phase of the operation where we're loading propellants, that
all operators behind solid cover.
Now you just heard a call out for operators going behind solid cover. When we fill the system...
Copy. We have bad news from the control room. The number one Boilermakers have unfortunately lost to Rutgers on a buzzer beater shot by Rutgers. We lost by 2 points. We're all down, but we're going to pick it up. Don't worry. However, on the live stream as well.
I am sorry we had to deliver you.
Copy. We'll get the done tonight.
Yeah, you also just heard a call out for an unfortunate basketball loss to Rutgers University. The number one Boilermakers will probably not be number one.
Yes, that is a very sad time for us indeed. Hopefully we will do them proud by firing a rocket engine tonight. Do we want to talk about one of the more interesting additions we have? Are you aware of the PSP Piccolo?
Yes, the PSP Piccolo. So, on our first hot fire attempt, in addition to aborting, we had an anomalous methane fire in the lower engine bay, the lower airframe, as you can see on the stream. And to resolve this problem, we've made a couple of changes.
We're pressurizing the vehicle. We're waiting for PT-OXO1 to stabilize. Over.
In addition to shielding all our wiring with foil to help prevent it from melting and severing critical data and valve connections, We have also installed a nitrogen blower that we have named the PS Piccolo to blow inert nitrogen gas into the lower airframe and prevent fires from forming.
Okay, we're stable. Go ahead and check for leaks.
You just heard a
Copy,
call
we're
out.
entering port yard.
You all just heard a call out for vehicle being pressurized. At this point, the vehicle liquid oxygen system has been pressurized with nitrogen, and the crew is moving out to the courtyard to try and identify leak rates by sound and by using Snoop. Snoop is essentially soap, and by spraying Snoop onto the rocket at certain locations, they can observe where leaks are.
I really have a very significant audible leak.
And obviously,
Copy. We're gonna go ahead and vent so you guys can tighten it.
Copy.
obviously, the call out that we have a pretty significant audible leak is never good. But one of the things that you have to do is vent before tightening. And is there any particular reason why tightening
prepare
under
for
pressure
vent.
is
Over.
so hard?
So the force balance when you're tightening under pressure involves gas also pushing against the force of you trying to tighten a fitting connection. And in addition to that making it harder, there's also the possibility of a fitting connection becoming undone under pressure, which is a dangerous situation.
Go ahead and tighten the fittings. Over.
Copy.
So one of the things that, as I'm sure you're hearing, is the giant nose in chat. This is unfortunately because we lost in basketball tonight. The number one Boilermakers was defeated by Rutgers in a buzzer beater, and that is something that we all take very dearly and close to our heart. It's a quite unfortunate time, however, we are working in their memory, quite frankly, to fire this rocket tonight. So right now we're tightening a lot of stuff in the lower fin can. What is the real purpose of the lower fin can on our rocket overall?
So below the propellant tanks, we have an assembly known as the lower fin can, and the fin can houses a number of critical fluid system items, as well as the name suggests, mounting points for the stabilization fins, which are not currently installed. So important components in the lower airframe include the run valves. So by actuating these run valves, we are able to start up the engine. In addition to that, we have our main method of mass flow control into the engine. These are cavitating venturis. And so these are just a couple of the fluid connections that we have in the lower airframe.
Right. We're also going to be able to debut some new technology on stream, and one of the many things you're going to be asking us is what certain things are on the rocket. So, if I can draw correctly, right here we have our lower fin can. This is the section we were just talking about, and I feel it's only proper. Next we go up the rocket, all the way up to the upper fin can. And what does this area do, and what is so important about the tanks not only below it, but also the one tank above it?
So, our system, Boomie Zoomie B, is a liquid-propelled rocket, a liquid-fueled rocket that utilizes a pressure-fed design cycle. So the idea of a pressure-fed rocket is instead of having pumps to feed fuel and oxidizer into the engine, you use gas pressure from an upstream source. So in our case, we are using a high-pressure helium bottle and diverting that helium into the methane and oxygen tanks. Yes, the upper plumbing.
In the upper airframe or the mid airframe, it gets complicated. But yes, we see what you're saying.
So in the upper airframe, this helium is diverted down into each of the respective tanks through a regulator, which reduces the pressure from 4,950 psi to the nominal
Yeah, we
pressure
tighten the
of
loose fittings,
505
so we're ready to check again. Over.
So
Copy. We're closing TV aux 03. And can you load MRN201?
So again, just to go
Ever.
over.
Copy. Actually, do not do that. I don't know why that's there.
So, if you guys are wondering, we control everything from BCLS, which is located on the rocket right around here. It's actually a ground support system. And if you hear anything about loading regulator, good chances are it's there. We also have our condensing system for methane located behind this bottle farm. We have an alternate camera angle that's able to better do it. And then this is the overall rocket. So if we have a flame diverter at the bottom, and then the nose of the rocket as well as the...
Do you want us to retreat by solid cover? I might have missed your last. Over.
The nose cone and recovery is currently not...
Go ahead and retreat behind solid cover, please. Over.
The nose cone and recovery is currently not mounted. However, they are manufactured and were actually successfully tested this week, so we're really looking forward to that. The next thing we should probably talk about is why we retreat behind solid cover when we're pressurizing the tanks, even if we know the tanks are already going to work.
So this is just another precautionary measure. When you retreat behind solid cover, you're making sure that your operators are in a safe position at all times, because
Alright, all
pressure,
test operators are behind solid cover. Over.
gas pressure is essentially stored energy in a system, and the more energetic a system is, the less safe it is to be around. Especially when we're doing leak checks, you are adjusting the positions.
Hold on for a second. We're seeing a PT issue. Over.
You are adjusting the positions of fittings within the system, and that can cause what you previously believed to be a safe system to possibly become unsafe.
And so when we're really testing these systems, we don't want them to have the super high energy that is given to them by a pneumatic system. What can we do instead to test them in a low energy state, like hydro testing?
Yes. So previously to these two hotfire attempts and to our cold flow tests, we performed was called a hydro-proof test. And so what we did for that is we filled our propellant tanks with high pressure water and tested them above the pressure that we expect to see here in this test today. And by testing well above the pressures we intend to see in the test today, we have done what's called a proof, or proving that they are safe to use.
That makes a lot of sense. So when we're talking about where we are in the procedures, really, leak checks seem to always take the longest, and then when we transition into the actual procedures, it really seems to start and get going. Is there any reason why we spend just so long on these leak checks? Like, these leaks just seem to keep popping up in various different places, as well as all these different issues we're finally finding.
Okay, we're going to go ahead and press the vehicle. Over.
Copy.
So you can actually hear on stream right now, if you listen very carefully, the air rushing into the vehicle. This is why everyone's behind cover. It's a very high energy situation. Maybe the next thing we should really go over is why our fin can has a bunch of aluminum foil on it.
I think I mentioned this previously, but just to reiterate, in our last test, the first hot fire attempt, we had a methane fire spread up to the lower airframe. And in this airframe fire, there were wires put at risk of being burnt and losing data or critical system functions. Now, we have two strategies to mitigate this in the current configuration. Number one, we have aluminum foil shielding around the wires to prevent majority of heat from getting to them in the event of a thermal event. And the other system we have in place is the PS Piccolo,
Okay, go ahead and check for leaks. We're getting a pretty big leak rate. Over.
which is an external nitrogen blower. So by blowing nitrogen
Copy.
into the lower fin can, we can fill it with an inert gas which cannot catch fire.
And another thing to note that is less of a systematic change and more of a change in the way we think, we have actually begun to not route any of our cables near any valves or any connection points. This is because during the first hot fire, we had a number of cables that got burnt that we believe could have been avoided with better routing. So if you see any of these cables be routed in lower directions or just ways that don't seem ideal from a routing perspective, it's actually to avoid
Can you guys
what
go
we
ahead and
believe to
check
be
the
hot
aux
spots.
vent line? Over.
So when we're talking about our vent lines, we actually have two major vent lines that we are discussing. Oh, let me 1 second.
And can I ask someone to go ahead and check PTFU03? Over.
Is actually directly in your guys' view. I believe it should be right here is our first vent line, and then our second vent line, because this is an oxidizer and a fuel vent line, is actually behind everything, and it runs out.
Oh yeah, we found we see another big leak, so we could stop pressurizing the vehicle. Over.
Is there a reason we weighed down all of our
Copy.
vent lines?
Prepare for an audible vent.
Just in a sec, you'll hear an audible vent.
Can you also specify what you mean by check the aux vent line? Over.
Never mind. That's fine. If you found the audible leak.
One of the reasons we are paranoid about all of these leaks coming through vents or valves is oftentimes being left out in the...
Can you guys confirm you unplugged and plugged back in PTFU03? We're seeing it reading back to normal. Over.
We often see that when you're in this environment... Oh, I lost my train of thought. How nice. Anyways, there's a question in chat. Did the control team perform the necessary trajectory simulations?
Yeah, Ben unplugged it and plugged it back in. Over.
If they did, can they do them now?
Perfect. It's reading
You got
normal
this
again.
one?
We'll have to check in with the controls team on
I
that
got
one.
you. No, so during the sizing of the initial rocket, we actually have 3 different versions of the control system sizing that we use. We use a 1 degree of freedom model, a 3 degree of freedom model, and a 6 degree of freedom model. All of these models are used for various different sizing methods. So 1 degree is used for the initial macroscopic sizing of the entire rocket, and then once
We need a
6 degree of
9/16
freedom.
wrench to tighten the fitting that's leaking, so we don't have one out here, so we're going to look for one. Over.
Copy all.
So, when we use the 6 degree of freedom, it's really nice because it's able to give us things like expected trajectory bubbles, as well as safety zones. So if we go on a ballistic trajectory, what would happen to the rocket, and how much distance around us do we need? We also, as soon as we're done with tonight, we can plug the thrust data into our both 1 degree of freedom, 3 degree of freedom, and 6 degree of freedom models, and that will allow us to get an expected altitude given performance.
That's right, Aiden. And this Hotfire test serves really as a full validation of our system, so we can figure out what we need to improve before we actually fly this vehicle.
There are a few things missing from this Hotfire, namely avionics are not on board right now, as well as quick disconnects. However, we are integrating those separately and have been doing integration tests of those. We just feel as if for this Hotfire they are not necessary and an added point of failure.
In addition, the recovery system, nose cone, and fins are not present on this Hotfire test.
So do you want to kind of talk about the overall system and what our goal is with this program, like the competition we're working on?
Absolutely. So, Boomie Zoomie B is Purdue Space Program's second entry into the FAR Mars launch competition. FAR Mars stands for Friends of Amateur Rocketry and the Mars Society, and it is a joint competition to figure out, to determine if any student team can launch a bipropellant liquid rocket to 30,000 feet with a 2.2 pound payload and successfully recover it. There is an extra prize if the team can do this with a liquid methane and liquid oxygen propellant combination. And the team has previously designed and built Boomie Zoomie 1 and performed 2 Hotfire tests on that vehicle. However, after the second Hotfire of Boomie Zoomie 1, it was determined that the vehicle would not be able to reach the altitude target and that the vehicle would need to be redesigned. So, in fall 2019, the team began design on Boomie Zoomie B, a second iteration designed to reach that altitude target with liquid methane and liquid oxygen propellants.
And Swag a Strange Sun makes an excellent point in chat. We're really trying to get some thrust data out of this in order to estimate the overall performance of the rocket. Do you have... So why is it that when we design a rocket engine, it isn't exactly perfect?
So, when you design a rocket engine,
Alright, we tightened the fitting. That was loose. We're just going to quickly go over a couple of other fittings. Over.
Copy all. Let me know when you're done.
there are a lot of complicated fluid dynamics phenomena that occur. And part of this design process necessarily involves testing.
Copy, we're good to go ahead and repress.
There are only so many things you can determine from mathematically designing a rocket engine. You have to test it to figure out the rest. And so, from the data we will gather from this Hotfire, we can determine what changes we need to make to the engine to bring it up to the necessary performance parameters.
So we're gonna start condensing after these leak checks. We're actually about halfway through. But can you go
all test
over
operators are behind solid cover, over.
what exactly we're doing when we say we're condensing?
Copy, we're going to go ahead and press the vehicle, over.
So, out of the propellants on this vehicle, we have liquid oxygen supplied directly as a liquid, but for our liquid methane, we actually condense that from gaseous methane. So using a liquid nitrogen cooling loop, we run gaseous methane through a tank with this cooling loop on top of it, and by running it through this tank at a set pressure, we turn the methane into a liquid, and we use this liquid methane to fill the vehicle.
Vehicle is stable. You can go ahead and check for leaks.
Copy, running back out.
So we're currently in the lock system, but now we're moving on to the helium system leak checks right
It
after.
looks a lot better, but can you go ahead and check the aux vent line? We just want to see if the valve is leaking through, so just like put your finger in front of it and see if you feel anything.
So why is it that helium seems to be more leaky? And of course we're testing with hydrogen, but helium really has this tendency to leak out everywhere all the time.
Yes, so we are testing with nitrogen for leak rates, but helium has a high leak rate because it is a smaller molecule. It's the second smallest
Just check the vent line and we looked at
periodic
it.
table, and as a result, it has a tendency to leak from small connections.
Can you repeat that? Over.
There's no leaking out of the aux vent line. We also don't hear any audible leaks on the rocket. Over.
Copy. We're going to go ahead and get a leak rate. Over.
So we're asking for an update what happened last hot fire. So during that hot fire, we have an automatic abort condition that is triggered based off of a sensor reading, and the sensor did fall off nominal, and we've investigated that since. And yeah, that's pretty much it.
It appears to be stable. We're just going to give it another second or two.
Copy. Yeah, we souped most of it, and we don't see anything. Over.
So, when we're getting these leak rates, what are the procedures that we go about in order to try and estimate a leak rate over a given time?
So one thing we can do for a leak rate, so what we can do is we can isolate the system, and by closing off all connections to that system and essentially leaving it as a closed volume,
It's looking really good.
we can determine, by looking at our pressure transducers, we can determine how much the pressure has fallen over a known amount of time. And by looking at how much the pressure has fallen over that amount of time, and by knowing the volume, the enclosed volume, we can determine what that leak rate is.
Query, can you close MVN 203?
MVN 203 is closed.
Query, prepare for an audible vent.
So one of our recent developments in our overall setup in terms of streaming, as well as just documenting what we do remotely, has been the ability to have a remote audio connection. This is obtained via an Axis webcam that's giving us all the data we need. Can you kind of talk to why remote audio is important, whether it be immediately telling relief valves or verifying vents or any other weird phenomena that might be going
Okay,
on?
we are through LOX leak checks. We are moving on to helium system and vehicle leak checks. Over.
So as you can see, we have moved through vehicle leak.
Courier,
checks at
can
this
you
point.
verify MVHO1 is closed?
MVH 01 is closed.
I
Courier, can you open MVN204? Over.
MVN 204 is open.
Courier, can you verify MRN201 is loaded to 100 psi on PGN202?
MRN 201 is loaded to 100 psi.
Copy. Courier, can you fully increase MRHE02? Over.
So, in case you're wondering, what do some of the different initials mean? So,
MRH 02 is open.
MR, all that
Go
sort of
ahead and
stuff.
check
What are
for
we
leaks.
referring
Over.
to when we say open MVHE02, for example?
So that's a
We don't
labeling
hear any
system.
audible leaks.
That is a labeling system we use for all the different valves and fluid
Can you repeat that?
components.
Did I hear no leaks on your end? Over.
No leaks. Over.
Can you repeat that one more time? Make sure you're holding down the button. Over.
That is correct. We have no leaks in the helium system. Over.
Copy all.
So, one of the things that we're going to be working on over the course of this rocket.
Okay, go ahead, courtyard, and retreat behind solid cover.
How about you go over how
I'll
leak
wait for
rates
your
are determined
confirmation.
and kind of explain the exact procedures, how long we rest, that sort of stuff.
So, I think there's a great answer in chat already, but just to reiterate, what we do to figure out our leak rates is we pressurize a certain part of the rocket, and when it's we hold it at a certain pressure, and then we close off that volume to the rest of the system. And by looking at the pressure data over time, we can figure out how much the pressure drops over a known amount of time, such as a
All
minute
test
to 5
operators are behind
minutes.
solid cover.
And then when you know how much that pressure has
Copy, we're
dropped
gonna
off
go ahead and press the
with a
vehicle.
given amount of time, and you know the volume of the section you closed off, you can figure out how much has leaked.
So right now, as we stated, we're in the final stages of leak checks. Coming up next after the helium system leak checks is going to be the purges. So what happens and why do we purge the system after leaving it alone for a long period of time?
So purges are a really important part of working with any kind of rocket system, especially one involving liquid oxygen. So foreign object debris, or FOD, is a really big concern when it comes to any kind of rocket system. Anything that you don't want in your system can cause really big problems if it's left in there. So what we do is we flush a bunch of nitrogen gas through the system, and this will remove any kind of particulates and atmospheric air, including water vapor, that would be present in the system. And so this is really important when we get down to cryogenic temperatures, because that atmospheric water can actually freeze and clog things up.
And when atmospheric water freezes, how much damage can that really do to our system? Because I know we have a lot of tight tolerances on our valves and different connections. Is that possibly what's leading to the current leaks?
Yeah, it's possible. But one of the biggest considerations with frozen water or any kind of foreign debris in the system is clogging up a very tight toleranced hole, such as those in the cavitating venturi.
That makes a lot of sense. Now, there's also a number of tanks on stream. Do we want to go over what some of them are, like what some of the bottle farms are, or what purpose they each serve?
Yeah, so you can see there are a lot of bottles and tanks within the image. So, Aiden, if you want to pull up the drawings.
Sure. 1 second. Our tech ready.
All right, yeah.
Let's go here. There we go. So we're going to start with these bottles on this side. What are these?
So those are our helium bottles. Oh, sorry, those are our methane bottles. My bad. And those feed directly into the condenser. As we previously explained, those condense into the liquid methane that fills our propellant tanks.
And then we also have this dewar right here. I believe this is one of our nitrogen dewars, correct?
No, that is our LOX dewar.
Oh, yeah, you're right.
So that is, as I stated before, our oxygen is directly supplied in liquid form, and that is directly routed through BCLS through a remote fill system into the rocket. Directly next
Can
to
we get an
that,
update from the control room? Over.
to the right, we can see
We're waiting for vehicle pressure to stabilize.
our 12-pack of
Copy.
nitrogen bottles. And so this is the gaseous nitrogen that we use for things like purges, which we are about to do.
Yep, that makes a lot of sense. And why do we need so much nitrogen?
Well, number one, we have a large volume of the system to fill, and we also have to do it quite a bit.
Is there any other things we do with nitrogen, like actuating a valve?
Yes, we also use nitrogen for pilot pressure. So we have pneumatically actuated valves, or PVs,
We're letting it stabilize, but you can go ahead and approach the vehicle.
at many different
Copy, we're
points in the
approaching the
system.
vehicle.
Our run lines, fill lines, and vent lines all have actuated valves on them, PVs, and we use methane at a low pressure to turn these.
Yep, and one of the main things that enables us to do is we aren't using a solenoid that or any other stepper motor or something like that pushes a large amount of electrical energy through the system. There is one small exception to that, and that is the dragon valve. What purpose does that have when we're condensing, and where really is it, or what does it do?
So on our condenser system, we have one electrically controlled valve, as Aiden said, called a dragon valve. So this is what's called a needle valve, and this has a adjustable position to it. And we can, when we adjust the position of this valve, we can determine how much pressure we build within the nitrogen, or within the condenser system. This allows us to really precisely control the condensation of the methane.
Right. And this is really important just because we're doing this constant balance between the temperature inside the system, and that's controlled by the pressure and the boil-off point of nitrogen, and also trying not to freeze our methane, which is quite a difficult task because of the specific heat of methane and all of its freezing characteristics. That's why we need...
We don't hear any leaks, and we haven't found any from snooping. Over.
Can you repeat that? We're not seeing a leak on our end.
Yeah, we don't see any leaks either. Over.
Copy, we're good. To proceed.
So that's why we have an entire DAC as well as control panel dedicated just to it, and coming up here shortly after purge, we should see the condenser come alive in quite the spectacular fashion. Again, our overall system is on the very right.
So yeah, go ahead and load MR into 01 to 500 psi on PG into 02.
The right, the condenser, then BCLS in the middle, and then on the left, the rocket. Do we want to kind of talk about why we decided to make BCLS and what advantages it gave us over the launch trailer?
Yeah, so as a primer, previously PSP had been focusing on creating a launch trailer to house all the necessary ground support infrastructure to launch Boomie Zoomie B. However, we decided to pivot to a skid that we call BCLS. Which would be more easily transportable by loading it into trucks and keeping the system in small, disparate
is
chunks.
500 psi. Over.
That makes a lot of sense.
Copy. Go ahead and retreat behind solid cover.
So when we're working on this overall
really
system...
quickly before that, verify MR HEO2 is fully open and reads over 500 psi.
One of the main things that...
Copy, MR HE02 reads over 500. Over.
One of the main things that we're really working on is making sure that our system is not as error prone as it was in the past, and one of the ways we do that is this constant readout of procedures, cross-checking, and everyone actually has a check of how it works. So one of the things we're going to be working on here is we're moving over from the helium leak checks to the vehicle purge, but before that, everyone's cleaning out of the area. Why is that?
All test operators are behind solid cover. Over.
Oh, we actually have a good question in chat that we can go over. What kind of load cells are we using? And yes, it is a pancake. What are we using for DAC? We use an NI USB DAC that is contained in a custom enclosure. And we did not use any open source Arduino structures. This is all done through the lab standard. We operate out of Zucro Labs, which is the most advanced university propulsion lab. And what we do with that is we make sure to follow all of their procedures exactly, as well as the way they set up their overall system. Do you want to kind of talk about what we kind of do at Zucro Labs as, from a higher level perspective, and what Zucro Labs is working on?
So Zucro Labs is the official propulsion lab here at Purdue University. Zucro Labs was founded back in the 50s and 60s, and kind of the main goal of this is to do tests on combustion parameters for engines. So other companies come work here, and then we also have the great privilege of being able to operate out of Zucro.
Yeah, and it's really one of those things. We have a number of companies. If you see our website,
Vehicle pressure at 400. We're almost there.
We won't mention them on screen in case any of them are non-public, but we have a number of great companies that work with us, doing a number of great technology, really pushing forward what we can do with propulsion in both commercial and research sense. And then, as you're of course hearing now, we are pressurizing the vehicle. This is always a good, or a stressful time, I should say, but we've done it so many times, and with the simulations it should be good. We do have a question here. How long do you purge the methane condenser between test days? And I think the answer is just this purge, unless I'm mistaken.
Yeah, it will just be this purge. I am not completely sure about the exact time interval, but you will hear call-outs and you will hear the purges on the stream pretty clearly.
Yeah, and the reason we don't feel it's necessary to purge the methane condenser is it's constantly hooked up to a LOX clean system, and in that system we make sure to tape or cap off every single entrance and exit, so we have a reasonable expectation that there are no organic matter moving in or out of the system.
That's correct, and the ideal is that everything is capped up or connected to another part of the system. Tape is only a temporary measure. And
we aren't just using any tape. What about blue tape? How would you describe it to someone who has never seen it before?
Essentially, it's a low residue form of tape, so that when you tape up an entrance, you do not leave any kind of sticky residue behind.
We're looking pretty stable. You're good to go ahead and approach the vehicle.
Immediately thread.
Copy, we are approaching the vehicle.
So we can see everyone approaching the vehicle. They are currently emerging from behind a very thick concrete wall. We can unfortunately not show the area that they are coming from, but it's critical to their safety that we keep each other through concrete walls, just to make sure that if anything does go wrong, everyone is safe. However, this does mean we need to use an awfully high-powered radio system at the lab. And can you kind of go over some of the issues we've had in terms of interference with these radios?
Yeah, funnily enough, when we use the radio here in the media room, it actually turns off the monitors for the stream.
Yep.
So we will not be using the radio in here at any time.
And another thing is, anytime we use it close enough to the DAC, all of our sensors jump around randomly. So if you ever see someone, they'll often be reminded to move away from the DAC. Or oftentimes, we will just try to have someone that has the microphone or has the walkie-talkie away from the DAC. Right now we're doing some leak checks of the overall vehicle. This is really just the top and bottom of our common bulkheads. Do you want to go over what a common bulkhead is?
So our system, Boomie Zoomie B, our propellant tanks have what's called a common bulkhead. That means that the bottom of the liquid oxygen tank is the same end as the top of the methane tank.
Are you hearing any audible leaks? Over.
Leaks on the vehicle, but there's one leak on GSE that we just found. Over.
Boomie Zoomie B stands for, BZB stands for Boomie Zoomie B. This is the second iteration of the Boomie Zoomie rocket.
The name is...
Hold for a second.
Long and storied, but needless to say, Rocket 3, which is our upcoming project that is in the works with a lot of our new members, is free to choose their own name as they feel fit. What we are currently doing right now is just some final leak checks on the system. It sounds like everything's going well, which is a real relief to hear. So, what are the roles of each of the people in this operation? We have people out here, we have the person we're hearing over the radio, and then we're also having people control the actual system.
Yeah, so the aim of this is to keep the process organized and make sure that everyone has a defined role that they have to play, and that people are...
So we're getting a leak rate of 2.5 psi a minute. We're going to go ahead and vent so you guys can tighten the GSE one, though.
People are going where they need to go, and that no one is accounted for in the operation. So, over the radios, you can hear our data systems operators, or DSOs, and our test conductor.
We're accepting the 2.5 a minute, but we're still going to vent so you guys can tighten the GSE one to make that more clear.
And at the moment,
Yep, that was understood. Over.
At the moment, we have test operators out performing duties in the courtyard.
And so, what kind of safety training do you have to go through to make sure you can work on this rocket?
Zucro Labs is a mandatory safety training where we learn about the dangers present at the lab. We also have internal trainings teaching members on how to perform assembly tasks, such as creating propellant lines, successfully LOX cleaning all the components in the system, and tightening fittings and doing things such as instrumentation system wiring.
And this is one of those things where we're able...
Okay, go ahead and prepare for an audible vent.
We're able to bring...
Copy.
We're able to bring in the newer members and have them working on something that is critical to the rocket. As you can tell, that is one of our more audible of audible events. This is because it actually went up to 500 psi instead of the previous pressures we were leak testing at originally. And of course, it's good to see everyone from the various rocket teams joining us. It's always an honor to have people watching and, doing the standard with our live stream. If you have any questions about how this live stream is set up, feel free to put it in chat and we might be able to answer it later. Or I'm sure we have a contact info on our website that you can reach out to us and we'll hopefully be able to get back to you. We're always...
And also to tighten the fitting that we found leaking on GSC, we're going to have to take down kind of like the black cap pressure, so we're going to have to deload MRN201, then vent out of MVHE01. Over.
We're always interested in expanding university rocket capabilities to every university that wants it. So, just this other day...
We're going to be unloading MRN201 pretty soon. Do you want to just wait for that?
We had a group of, I believe, 7th graders? Or maybe elementary schoolers.
Right,
but they came through, they helped us test our force cell.
Copy all.
They helped us test our force cell by hanging on the rocket, and overall it was a great time to see some of the younger members of our rocketing community. Next up, we have a question. Which propellant leads during startup?
Courier, go ahead and unload MRHE02 and MRN201.
We'll have to get back to you on that, but I believe off the top of my head, and maybe one of our people that are watching has a better idea, our fuel line is slightly slower on the actuation, so the LOX ends up leading. We're trying to really hit them both at the same time. We don't want something leading over the other. In reality, we're just trying to avoid hard starts and all the trouble that comes along with it.
MRHE02 and MRN201 are unloaded. Over.
Copy. Go ahead and open MVHE01 to vent the system. Prepare for an audible vent.
MVHE01 is opened.
Once PGHE01 reads ambient, go ahead and close MVHE01.
HE01 is closed. Over.
So, the issue you probably just noticed is walkie talk over.
Okay, then go ahead and close MVN204.
Are you familiar with the system, but what happens when you're talking over someone?
MVN204 is closed.
So, when someone is
Copy,
talking,
you're good to go ahead and work on that fitting.
when someone is talking over a walkie-talkie, because it is at this point, it's a digital protocol, you actually have to you have to have only one person go at a time for proper decoding and encoding. So if two people try to simultaneously broadcast, bad stuff happens, especially across...
And also just as a note, PVFU03 is leaking a little bit out of the actuator body. Over.
Okay, noted.
So, what's the difference between the actuator of a valve and the actual valve itself?
So the actuator is essentially the thing that drives the valve, and so that doesn't actually see any liquid flow through the system. So that is just nitrogen driving it so it can turn it back and forth. Now that is connected mechanically to, in the case of most of our valves, a ball that will turn and actually expose the liquid to the flow path.
So right now, we are of course debugging the BCLS system. Is there anything you want to talk about in terms of the overall rocket? Like, for example, some of the manufacturing challenges we had, or perhaps how it's mounted to the I-beam itself?
Yeah, so I can go to one of the manufacturing challenges we had on the rocket. So building a common bulkhead rocket has a couple of design decisions that go around it. So because the tanks of our rocket are also the skin, that means that you have to route plumbing connections either through or around the outside of the rocket. And for us, we really wanted to minimize the drag forces on the vehicle. So what we elected to do to get our methane our helium down into the methane tank, which is below the LOX tank.
Our Declan tightened that one fitting that was leaking, and we're ready to proceed. Over.
Is to run propellant.
Copy all. We're going to go ahead and proceed with system purges. We are officially through leak checks. Over.
You just heard the call out that we are officially done with leak checks and moving into purges. After that, we will move into propellant condensing and load, which will be much faster.
Yes, leak checks take the majority of our operational time while we're streaming. Of course, this...
Clear, can you verify PBF-U05 is open?
And so, the longest part of our setup is actually the time of the day before we go live with the stream. We've been actually preparing this since about 2 p.m. today. And then
PBF-U05 is open.
Can you go ahead and open MVN204?
MVN204 is open.
Load MRN201 to 100 psi.
ETA for Hotfires whenever we get through procedures. However, it should hopefully be coming here soon. We are speeding up, but
MRN201 is loaded to 100 psi.
But to say that I had an idea
Fully
would be
increase
wrong.
MRHEO2.
So of course right now
MRHE02 is open. Over.
we are just getting our bulk nitrogen ready to
Go
purge
ahead
through
and
the system.
close MVN201.
MVN201 is closed.
Go ahead and open MVN202.
MVN202 is open.
Open MVN203.
MVN203 is open.
You just heard at least one actuation. Oh, there's two. So how do we make sure with these constant readbacks that we don't have any miscommunications between the control room and the people or test operators out in the field?
Courier, go ahead and open MVN201 to begin the nitrogen purge. Wait 15 seconds to purge the system, and then repeat this step 3 times.
So
Copy, we're starting the first purge. Over.
this is where the importance of knowing and following procedures comes in. All of our operators and test conductors and data system operators have the same procedures in front of them at all times and are constantly checking off steps to know exactly where they are in the procedure. And so everyone's able to follow along and be on the same page very easily in a rehearsed way.
The first purge is complete. Over.
Copy, proceed to the second.
So, you heard the first of our 3 purges, and as you just heard, they are 15 seconds each. This is purging our entire system through BCLS, and that was one of our major advantages when we first set up BCLS, because it's designed to have an integrated leak check system that we can do without using propellants, as well as this purge system. And can you kind of give us perspective comparing the old system to the new one, just what, like the amount of movement you needed to do an operation on it?
So we've
Alright, second
definitely
purge complete. We're going to continue with purge 3 and 4. Over.
we've improved not only
Copy,
the
you're all good on
design.
our end.
We've improved not only the design of our system, but also the procedures have drastically improved. Not only since Boomie Zoomie 1, but also since our beginning of working with BCLS. We've really gotten to be familiar with the system over our, I think this is 8
It's either 8 or 9 operations.
8 or 9 operations with the full system at this point.
Yeah. And it's one of those things where this number of operations is necessary to really hammer out all the little small details that we miss, or there's just something wrong with the system that we want to make perfect because
Alright, third purge complete.
before we start this
Copy,
massive
proceed with
cost
4th.
of buying propellants. I guess we will be leaving you towards the beginning of propellant load, so we should really start talking about what you should expect to see in terms of condensation, the clouds billowing off the rocket, and we can start all of that with the most immediate, which will be propellant condensing. What are we expecting to see?
So when we start propellant condensing, you'll start to see atmospheric air basically forming clouds on the lines and on the condenser itself. So when we show camera views of that, it'll start to get really cold and you'll start to see ice and snow forming on the outside.
Alright, all the purges are complete. Over.
And then after that, once we start
Copy all.
rocket chilling and loading, you'll start to see the tanks on the rocket get progressively colder, and see ice and snow forming on them as well.
Heading close TV SU05.
I am not aware of the exact amount of methane we lose while condensing. However, we try to make it minimal, and we can control that by sealing the system until condensation starts. And then, by the way our system is designed, do you want to kind of go over how the heat exchanger works in the bottom? Or
Yeah, so essentially we have
TVFU05 is closed.
we have an outer jacketed tank to our condenser, and then an inner tank that our methane actually goes inside. And we have a coil of tube going around the inside tank. And by flowing liquid nitrogen through that tube, it causes heat transfer into the wall
Close MVN202.
and can chill the entire concentration.
MVN202 is closed.
Courier close MVN203.
MVN203 is closed.
Courier close MVN204.
MVN204 is closed.
Go ahead and open MVN201.
MVN201 is open.
Unload MRHE02.
MRHE02 is unloaded.
Load MRN201 to 150 psi on PGN202 for fin can purge.
You just heard her call it for fin can purge. So this is using the PS Piccolo, as we have deemed it, to blow inert nitrogen into the lower airframe. This will mitigate the risk.
MRN201 is loaded to 150 psi.
This will mitigate the risk of fires in the lower airframe as we.
Awesome, we are
fire
moving
the
on to
engine.
propellant condensing and preload. We're moving on into an igniter installation. Over.
so we are now
Copy.
installing the igniter. This might look a little primitive with a stick, but why don't we just use a stick?
As Aiden just stated, for the ignition system of our rocket, we don't use anything fancy. We
Okay,
literally-
and for everyone on Liquids, we are doing our official shift change right now. So you know who you are if you are shift changing. Over.
You also just heard a call out for shift change. We are changing out our operators and shadows at this point in the procedure.
The operators have been going for a very long time today, and we found that it's better to have a set point where operators switch off in order to remove any confusion and make sure we know where everyone is at all times. So, circling back around to the injector installation, what's really going on there?
So, yes, as we stated before, the igniter is simply a chunk of solid propellant on a stick, essentially, with an E-match connected to it. We found that this is the easiest and simplest way of starting up our rocket and igniting the flow. And it has worked for us in the past very well. We found really no reason to complicate a system when we can just do it the easy way.
It makes sense the Russian Soyuz does it. They were quite good at figuring out how to ignite rockets. And igniting rockets in any other way is quite difficult.
Yeah, it drastically simplified the design of our system.
If you have a reignitable engine, it's effectively another engine, right?
Yeah, so regardless of whether you use a torch igniter or something like a T-Tab start package, you really add a lot of complexity to your engine. And we wanted to keep things as simple and cheap as possible since we are a student team.
Right. And that's really what we've learned in this rocket, is we have to keep it as simple as possible. As you can see, I think we're approaching for probably the igniter installation, and we will see what's going on there in a second. Another thing you might notice is people walking around in it's cold outside, but when interacting with the cryogenic systems, they're wearing some special clothes. What type of clothes are those?
Yeah, so you do need special personal protective equipment, or PPE, when working around cryogenic liquids such as liquid nitrogen and liquid oxygen. So this involves a face shield to prevent any liquid from splashing on your face and damaging yourself, and also wearing special thick gloves to protect your skin from cryogenic burns when handling very cold objects.
How cold is cryo?
Well, depends on the fluid you're working with, but I believe our liquid oxygen settles at around negative 297.
Just like from a higher level view, what is cryogenic cold for those that haven't experienced
it? Is extremely, extremely cold. Much colder than any outside temperature you'll ever experience.
What does it do to the air around it?
So cryogenic temperatures will actually make clouds in the air around it. So when you see what seems like smoke or steam coming off the rocket, it is literally clouds, the same thing as up in the sky.
And as you can see now, we are working on this Hotfire, the igniter installation. The good old piece of tape. We actually today found our igniter sticks from last Hotfire, so there's a chance we are reusing them. I don't know for sure, but it is possible. We moved actually from redundant igniters to just one. Why? Do you know why that was?
Yeah, so after our last Hotfire, we determined that having that redundant capability was not necessary. Both of them fired and so we decided to move, I think, to redundant E-matches instead.
Yes.
And there was actually a risk presented by having redundant igniters. By having both of them in there, one of the igniters actually swung out upon ignition and ignited methane in the lower fin can bay.
Right. And can you kind of talk about what happens when a rocket engine is ignited?
So when the rocket engine is ignited, you have your valves actuate and propellant will flow into the injector at a high pressure. And then our injector, what is known as a pintle injector, will inject the liquid methane and liquid oxygen in a spray, and these sprays will mix, and then the solid propellant will ignite this mix.
Can someone check if the leak at PBF-03 stopped when we opened it over?
Cause the entire engine to come up to pressure, and then basically blow the igniter out the bottom of the engine.
Right. And this is all a really complicated process, obviously. How would you learn about rocket engine ignition? Is there like a book you recommend, or?
Well, for a book on general rocket design,
I believe the leak is out of PV-Ox-03 right now.
I think.
Can you repeat that?
The leak is currently out of the PV-Ox-03 actuator body. Over.
I recommend a couple. Rocket Propulsion Elements is a classic. For kind of a more casual history, I would recommend Ignition by John D. Clark. And then, just repping Purdue, Heaster's Rocket Propulsion is also an excellent subject.
I can confirm that is an excellent book. One of the things we're working on now is just this overall igniter installation. When we are traveling to Hotfire,
opening
PV-Ox-03
is there anything special we have to do with
these
over.
igniters? Is there any storage that we have to do, or what really are
Copy.
these igniters?
Can you go and check for the same thing
At a high
on
level, of course.
FU-03?
Yeah, so like you said,
We
these
don't currently hear a leak on FU-03. Over.
these have to be treated essentially like small solid motors or
Copy all.
explosives because they contain both a small amount of solid fuel and oxidizer, so they could light on fire at any time. So we do have to keep them in strongholds while we transport them.
Yes. And they also have to be shorted during the entire journey if we install them beforehand.
There are a lot of transportation difficulties that we've had to figure out during this project. Moving an entire system from West Lafayette, Indiana, across the country to the Mojave Desert in California.
Do we have someone installing the igniter because we have steps to go through?
Yeah, we started installing the igniter. Over.
Sometimes, this is actually, we don't often install igniters, so it seems we've deviated
Okay,
slightly,
I'm
but
going to
we'll
go ahead
get
and
back on
verify
step.
some things at the courtyard. Can we verify that the igniter leads are disconnected from the igniter Wago block?
We will be putting the books in
The
chat
leads are
right
disconnected
now.
from the Wago block. Over.
Can we verify the continuity across the igniter leads with a multimeter?
The Wago block is the connectors we use on the rocket. So they're just simple, easily accessible connectors that you don't need any tools to use. And that's what really makes it nice. You have to just have a ferrule on the end of your wire, and then you can just
Continuity
plug
on the
stuff in
igniter
and
is
out.
good. Over.
Copy all.
And yes, we are getting the book names in the chat now. From a variety of sources all around.
Verify the igniter Wago blocks read 24 volts DC using a multimeter.
So what we're doing right now is we're just verifying that all of our systems are go, and making sure everything goes okay. So there's all the book titles you had, and how did you first learn about rocket propulsion and like go through some of your experience with that?
Well, I guess kind of from a general level, I think PSP has done a great deal of teaching me about these things. I have really mostly focused on the
Can
fluid
you validate
systems
that we have power going to both igniter Wagos? We only see voltage on one. Over.
side of things here at PSP, but I think
We only have power going to one. Over.
the thing we shine most at is learning by doing here. Really, the best way to gain practice on
Copy.
these
Can you
things
bring power to both? Over.
in the context of a student
Just
team
did. Over.
is to
We
take a
have now
step
reading
at
voltage on both. Over.
Yeah, I definitely agree with that. And one of the special things about our organization is our undergrads who are then mentored by graduate students. And that really allows us to have a lot of new people learn. We actually had a record recruiting class this year. I think it ended up being about 150 people. And that's really what has allowed us to do all this amazing stuff, is the work they put in and all of our current members put into making this operation happen.
Yeah, and also a lot of support graciously coming from Zucro Labs and staff that help us out at every turn. This would not be possible without them.
So, you play Kerbal, I play Kerbal. I think it's near 100% of us that play Kerbal, right? I think there's like some, but like, what would you say, 95?
It's definitely been inspiration for a lot of the team. Yeah.
Yeah, NASA, yep.
Michael Colenti has another terrific recommendation in chat. Huzon Huang is a terrific source to really get to know liquid rocket engine design. And it is completely free.
Yeah, that's one of the great things about it, is it's an old NASA document, so there's a lot of really interesting things in it. I believe it's also the fully declassified version now at this time, so there are some additional things about turbo machinery, but I could be incorrect. Right now we're just doing the installation.
We have an update. We currently have one Wago block has a voltage and one doesn't. Over.
Both are on. Over. We have Spark 1 and Spark 2 energized.
So, this is why we have backups. It sounds like we're having an issue with the Wago, so we're going to be working through that shortly and trying to figure out what's going on. Do you want to talk about some of the
Alright, both are energized. We're good to move on. Over.
the thought process we go through when working through issues we have on the team?
Specifically when it comes to operations.
Are you confirming that both read 24 volts? Over.
Both igniter Wagos read 24 volts. Over.
Specifically when we are running operations, it's really critical that we engage by first saying what the problem is and then working the problem logically and methodically.
And we got another great question.
Copy. We have deactivated sparks and activated safety again. Courtyard, please go ahead and verify the igniter Wago blocks are reading 0 volts.
Another great question is how many of us daily drive Linux? And I think the answer is almost none of us.
I know one of us does for sure.
Got it. The reason why is SolidWorks and ANSYS don't work on Linux.
And
Both
MATLAB
igniter
doesn't work.
Wagos are reading 0 volts.
Yeah,
Over.
so unfortunately those are the critical softwares we use. They're great sponsors to us, and we really
Copy.
couldn't live
Go
without
ahead
them.
and install the igniter stick in the test article.
So we should be seeing,
The igniter stick is installed in the test article. Over.
if you could see through
Copy.
people.
Go ahead and install the igniter leads into the igniter Wago.
If you could see through people, you'd see our igniters being installed right now, and then being clipped into the Wago connections that we use in order to make them easy to both connect and disconnect. I think we're approaching we are getting very close to propellant condensing here. Do we want to kind of talk about some of the challenges we had when we were first doing condensing.
Yeah, so one of the issues we had doing our first cold flows was that we were not supposed to cold flow with the actual propellants we were using. When you are doing a test to validate your system and you don't want to actually turn on the engine, you can't use the actual fuel and
Both igniter leads are connected, over.
that you plan to test with, because those can mix and start a fire
Copy,
outside
go
the
ahead and
system.
verify and give that a tug test for me, and verify the igniter is installed in the thread, over.
So our first cold flow test used liquid nitrogen as kind of an analog to make sure that our system did
Alright, we
well in
verified that the
cryogenic
igniter is installed
conditions.
properly and that the leads are connected, over.
But for subsequent
Copy all, we're
cold
moving into
flows,
pre-test on our end, over.
subsequent cold flows where we had to demonstrate the condenser, we needed a fluid that would closely mimic the properties of liquid methane. So for this, we decided to make the uncommon move of condensing argon gas into liquid argon.
Can we
gas.
verify everyone in the courtyard is wearing high pressure PPE and that all propellant doors are closed and that there's no pressure in the system?
You can also see on screen, I know we had the question about it, at the end of the twisted cables, you can see 2 Wago connectors, and that's what we use to connect. Do you want to talk about, although I see there is some suggestion in chat to use Creo,
All propellant doors are closed and we do have pressure in the purge system, over.
one of the major benefits we get is PDM. So do you want to talk about what PDM is and how we can kind of teach new members it in an industry-relevant manner?
Yeah, so PDM stands for Product Data Management, and it's a software that we integrate with SolidWorks to let us have all of our members have revision-controlled access to our part drawings and documents, and also assemblies. So what we can do with this is prevent people sharing around documents individually and having out-of-date part drawings and CAD files floating around. What we have...
Okay, we're going to go ahead and move on to condenser methane load.
Woo!
Very important call out there. We are moving on to propellant condensation at this moment. Pretty soon you should start to see clouds forming and things start to get kind of exciting here.
This central column you see is the condenser, and as we discussed earlier, we're going to be slowly opening needle valves, normal valves, and our end goal is to see liquid nitrogen flowing out of the bottom of that tube, and that will tell us we have it all chilled in, and then we'll be able to start condensing methane out of it.
Yeah, so most of our procedures up to now have been leak checks. Most of the rest of these procedures should be chill in, and then after we chill everything in and start condensing, propellant load and vehicle pressurization will happen very, very quickly.
We will see what we can do about the overexposed camera. Not much we can do, unfortunately, as they aren't physical cameras. This is all a LoRax security system, but we'll see what we can do in the settings. We want to make sure we're capturing all context, including critical relief valves. Now, have you heard a relief valve actuate before?
Yeah, they're quite loud. So when you hear relief valves actuating on stream, you'll probably hear a pop and a hiss after that.
Yes.
And you might hear that repeat. And that's a very normal thing when our system's being filled.
So, that's an excellent question. We pride ourselves in safety. So, when do all personnel leave the area?
Once propellant load starts, no one will approach the vehicle until after the vehicle is fired.
Correct.
We really think that it's important that once we have those propellants in close proximity to each other, that poses a large risk to our operators, and we don't feel comfortable letting them around it. So we have a lot of safeguards in place to make sure that we can do this in a safe manner.
Right.
Clear, can you verify PBSU05 is closed?
PBFU05 is closed.
Copy. Can you go ahead and open MVFU01 carefully?
Looks like we are beginning condensing now.
It's the methane bottle.
So these are methane. We're opening all the
We have a
bottles and
valve
shoving it into
on
our system.
condenser labeled MVFU01, but we'll go ahead and open the methane bottles, over.
That's not the methane bottle. It is MVFU01.
Alright, MVFU01 is open. Should we open the bottle?
Do not open the bottle. I'm sorry, I had an operator trying to talk over me.
As is life in the control room, it's often we try to keep it as controlled as possible, but it is one of those situations where you need. That's why we have procedures to make sure we check any errors. One of the things I guess we should really talk about.
Can you verify that the methane bottle farm is closed? MVFU02, MVFU03, MVFU04, and MVFU05. Over.
The methane bottle farm is closed. Over.
Go ahead and open MVFU02.
What type of concrete, or how are we even surrounding this to make sure it's safe in case it does detonate? And where are we in relation to this to make sure all personnel are safe?
Yeah, so what you can see here is the courtyard where we have the vehicle and ground system assembled. This is in
MVFU02 is open and we hear no audible leaks.
In thick concrete walls. For additional protection, the vehicle itself is behind
No audible leaks, correct?
concrete blocks.
Correct.
And then when the test operators
Copy. Go ahead and open MVFU03, MVFU04, and MVFU05.
when the test operators start propellant load,
Those are the bottle farm valves.
everyone will move into a completely different building, which is very far away from the rocket. So it poses no danger to the crew.
We have multiple thick walls of concrete in between us. That's actually why, again, our we have.
All bottle farm bottles are open. Over.
Copy. Can you verify PGFU01 reads over 1,000 psi?
With the walkie-talkie power, it's because we need it for
PGFU01
the
reads
overall
2,000 psi. Over.
We're gonna take a quick break for 1 second while they begin to read.
Copy all. Go ahead and load MRFU01 to 100 psig on PGFU02.
We're going to be taking a quick break from commentary, and we'll leave you with the beautiful sounds of our operator callouts. Thank you, and we'll be right back.
MRFU01 is loaded to 100 psi. Over.
We are opening SVFU02 to load methane into the condenser.
All right, and we are back. We had a small technical issue with our audio source, so I wanted to get that resolved so everyone can hear it.
Prepare for an audible vent.
Hopefully, if this ends up working. There we go. You guys should now be able to rehear the system. So do you want to kind of talk about what's going on overall on the system?
Yeah, so just as a recap, at the moment, we are moving on to our propellant condensing. So, in the general timeline of things, what's going on here is we are condensing our methane from gas to liquid form. After we do that, we will load liquid oxygen and liquid methane into the rocket. And then after that happens, we will load our helium from the ground system into the rocket. Once we load our helium, our liquid oxygen, and our liquid methane, we will immediately proceed to our ignition sequence and fire the vehicle.
Okay, we're going to move on to methane condensing, so let's have someone don cryo PPE.
And there you did. There you have it.
Copy, Declan is donning cryo PPE. Over.
We just heard a call out for propellant condensation starting. You can probably hear the system starting to react at this point to nitrogen entering the system.
And this is one of the more critical phases of our operation. It's definitely we actually have to have...
We're going to move through these steps pretty speedy. Okay, load open MV-N210.
You actually have to have a very fine touch, and that's because we're currently balancing these points. Do you want to talk about what it's like as an operator to be messing around with the needle valve and trying to hit all
Load
the right points without freezing?
MRN203, fully open, fully increase it.
Yeah, operation of this condenser is remote but still very manual. So an operator has to sit in the control room and monitor pressures and flow rates to make sure
MRN203 is fully open. Over.
To make sure that our methane is condensing but not freezing. So this is kind of a juggling act.
Right, and...
Copy all, open MV-LN201.
What would happen if
that's the liquid valve?
So, if we froze methane in the system, this would be really bad. We do have filters within the system to catch
MV-LN201 is open, over.
To catch any solid
open MV-LN202, the gas valve.
But in the eventuality this does get into the rocket system, this could really mess things up by
MV-LN202 is open,
an injector port, or say our cavitating venturi's and restricting the amount of flow that goes to the engine.
Right, and how long, or what? We don't really know how long it takes, but what are the key factors we're looking for in the condensing operation?
So we want to make sure that we chill in the system first, to make sure that it's cold enough that we can actually start flowing methane through.
Can you close the liquid nitrogen valve, over?
We close PVLN201, is that what you want?
Yeah.
You see the line that is directly on screen now, the flexible hose, is the one
What's
going through
going
the
on
liquid
in
nitrogen doer. So this is the first cryo.
We just had like vapor coming out as LN2 vent. I think. Do you think the dump valve's open? Yeah. I think the dump valve's open. We're gonna double check it. Over.
We believe that is that sound is the liquid nitrogen venting. And as you just heard the call out, not exactly intentional, but that's again why we.
Yeah, the LN2 dump valve was open. We should add procedures to verify that. Over.
Yep, that's why we have these procedures in place, and also why we have skilled operators. They help each other in hand, and obviously we should have caught that, but it's something we can take forward to the next operation.
Over.
Do you want to go over how we vet these procedures?
So we have detailed procedures reviews and things called test readiness reviews with our advisors and Zucro personnel to make sure that we are actually ready to take on these tests and that our conditions in the procedures not only reflect what our system is going to do, but that it's safe to all the operators.
Okay, we went ahead and opened PVLN201 to begin LN2 transfer to the condenser again.
Believe you can hear it now. The LN2 flowing. Hopefully not flowing in a way we out the dump valves anymore, but now we're seeing some of that ice forming and the clouds that we were expecting earlier.
Yeah. So you can see the lines are turning white here, and that is definitely frost forming on the outside.
Right. This little bit of condensate, or the clouds forming, that may be a slight amount of leakage. However, given its position in the system, that's acceptable for us. Right now, this is just bulk nitrogen that we will be constantly flowing through and out the condenser to keep it right at the temperature we need. And right here, you actually see some of the cryo PPE.
Yeah, so like I said before, you have to wear very thick gloves to work with this system to make sure your hands and face are protected from any cryogenic burns.
We see a small liquid leak on the flex line that goes from the doer to the PVL-201 valve. Can we tighten it over?
Yes, go ahead.
I believe that is the cloud forming that we are seeing right now, is that small liquid leak they are referring to. So, when we're working with cryo, is there any special considerations about where you are compared to the vents, or maybe tank pressures, where tanks will automatically vent on their own?
Yeah, so when you're working near a cryogenic system, it's in any pressurized gas system, really,
Alright, we just fixed the leak. Over.
it's very important that
Copy
you
all,
stand
thank you.
away from the source of that gas pressure coming out. Because that, especially when it's really cold like that, you can impose burns on yourself.
Right. And one thing about gas dewars is they'll actually occasionally, if we're building pressure in them, will have relief valve events on their own. This isn't always intended, but it's what relief valves are for and is expected. So we're just trying to make sure everything goes smoothly there. Right now you're hearing the system going. This is actually because there's a vent valve pointed directly at the microphone. So we're going to turn it down a bit, but the vent valve you're looking for is one of the 3 L-shaped tubes that you see in the middle bottom of your screen. And what do we expect to see coming out of these tubes?
Yeah, so our vent lines will often have liquid coming out of them, especially at the end of an operation. It's very normal to see liquid coming out of these to just verify that things are actually moving through the system.
Right, and the good thing about having liquid coming out is because our vents are in the top of the system, we know that means that liquid is making it all the way through the system, which means we know exactly what temperature we're at, and we can begin methane condensing without having to worry about freezing or losing methane to the system. The next thing I guess we should talk about is why we have a valve next to every manual regulator, and what that's kind of telling us.
Yeah, so when we have a valve next to every regulator, that lets us really isolate the system and make sure that flow doesn't ever go back. It's very important to us that we isolate things with check valves to make sure that flow only goes one way when it needs to.
Yeah. And then, as you can see, the line itself has gotten quite frosty, and now this silver column, the condenser itself, is beginning to get quite frosty as well. We have a good amount of wrapping around all the smaller lines, but because of how the condenser is currently situated, it doesn't make sense, especially compared to the cost of operations. It doesn't really make sense for us to wrap it in something like fiberglass, because it just gets on all of your clothes. Have you had any experience with it?
I haven't myself, but it doesn't seem fun.
It stays in your pants, and you have to be aware of it, quite frankly, because it will make you itch for weeks anytime you wear those clothes. Exactly. We are letting the cold flow now. As you can see, another thing we have on this system in particular is standoffs, and long ones at that. Can you go over what the point of standoffs are in the system?
Yeah, so thermal standoffs are really important when you're working with a cryogenic system to make sure that when you're reading something like a temperature or a pressure, you're reading the temperature where you actually want to, and that you're not just reading the temperature in metal, I believe.
Yeah. And in valves, if the valves themselves are way too close to, or the actuators are too close to the valves, they'll actually freeze, and that is definitely something we want to avoid in this system. You may have noticed we have a lack of radio callouts right now, and that's because, quite frankly, we're just waiting for the system to get down colder. So we should probably talk about what's happening next. When we go away and we begin propellant loading, what should we expect to see on the stream in terms of will the rocket get colder? What will start happening in those final few moments?
Yeah, so in those final few moments, once we start propellant load, you'll start to see the tanks progressively get colder and colder. I believe we load methane first?
I believe so.
Yeah, so when we load methane first, you'll see the methane tank on the bottom will become cold and frosty first. Then once we start LOX load, the top tank will become cold. Then, afterwards, you will see a call out for helium load. Once helium load happens and we read good helium pressures in the rocket, that is go time, and we will start our auto sequence. Once auto sequence is started, the only thing we can do to the system is trigger a manual abort, or have an automatic abort, or have a successful fire. So once you hear the call out for auto sequence start, the fire is about to happen.
Yep, and we should be able to get a live control room over the walkie-talkies. They'll hold down the walkie-talkie buttons, and you should be able to hear a joyous countdown as we move towards that. And as always, it's great to see in the chat a good luck wish from a fellow Rocket team. Again, we are really into expanding the knowledge of liquid rockets and rocketry in general. We're one part of PSP, but do you want to kind of talk about the other branches of PSP we have and what we're trying to do as an overall team?
Yeah, so Purdue Space Program is an association of all of 7 different technical teams and other projects within PSP. So we have a liquid rocket team, a hybrid rocket team. At the moment, I believe we have no less than 4 different solid rocket teams,
Correct.
including a NASA student launch team, a Spaceport America team, a Space Shot design team, and a team looking to do active control of solid rockets.
Right. And all of these different teams, we really feed into each other. So due to the complexity of the system, we don't launch much. But when we have these other teams working on they're able to launch more with more avionics. They have more experience with recovery, but we might have more experience with the ground support system of specialized teams. So by working with the other teams, we're able to share resources and share this amazing resource that is Zuko Labs.
Oh, and I almost forgot there for a sec, our satellite team as well. We do have a satellite design team.
That is true.
Yeah.
Not rockets in the traditional sense, but they're the payloads. We often forget about that, but it's just as important.
Once again, appreciate the shout-outs in chat from our other design teams and from the other rocket teams.
And as previously discussed, you've seen the condenser started chilling down. It's fogging around there. A ambience has begun around the launch pad. You can see just barely in the bottom right of our wide view smoke wisping out, and that's an excellent sign that we are on our way to a full tank. Again, we have to fill this entire tank up so we know the exact temperature before we start condensing. I am not too sure of the exact details of our active control teams, but if anyone from active controls is watching this live stream, feel free to pitch in and let us know. Are you aware?
I'm not aware.
That makes a lot of sense. Each team, we work together as much as we can, but oftentimes the details of our projects are, we work together, of course, as separate teams. There you go, it's thrust vector control systems. And, we actually talked to Joe Barnard about stream setups, for example. He's probably the most experienced streamer out in our launch site. Do you want to talk about a little bit about that launch site?
Yeah, so we plan to launch at the FAR launch site out in Mojave, California. Sorry, the Mojave Desert in California. So we'll have quite the road trip to get out there. We plan to use FAR's campus as they are part of the FAR Mars launch competition. They have basically the only range in the United States where we can launch liquid rockets, especially to the altitude requirements that they have mandated.
Right. Liquid rocketry is a lot harder than any of us, quite frankly. I mean, everyone knows rocketry is hard. This has been harder than we expected. I guess now is as good a time as any. This is BZB. Why did we hit Far Mars with BZ-1? Specifically, helium system, and, you know.
Yeah, so Boomie Zoomie 1 had 2 successful hot fires.
That, by the way, is the control operator now going ham with a manual valve, or possibly setting the needle valve in order to get exactly the pressure he wants. I believe it is Braden is controlling that right now. He wants exact, is it more?
It's Braden.
Oh yeah, that one's on Braden. So our 2 operators, we have 2 DAC systems. Do you want to talk about them?
Yeah, so for our control room setup, we have a test conductor, and then we have 2 data system operators running the setup. So the data system operators are looking pretty much at data readouts and confirming that everything looks nominal. The test conductor really overseeing the entire operation. And then out in the courtyard earlier, you saw all of the test operators actually out turning valves and tightening fittings and making sure leaks don't appear.
Yeah, that's really what one of the most critical things is. We make sure to have people in the places that they're trained, while also training up new people in order to do it.
Looping back to your earlier comment, so Boomie Zoomie 1 had 2 successful hot fires, and it was determined that Boomie Zoomie 1 cannot meet the stay and altitude requirements. And one of the major reasons for this was A, an undersizing the propellant tanks based on what was needed, and B, an undersizing the helium system. It was not realized in the BZ-1 development program that when helium comes into contact with cold propellants, cryogenic propellants like liquid oxygen and liquid methane, the helium will actually contract and effectively become smaller. And this makes it harder to pressurize the vehicle. It means you need to bring along more helium with you. So one of the key improvements we made in the BZB program was enlarging our propellant tanks as the requirements dictated, and also dramatically enlarging our helium system.
Right. And as you can see on the stream now, in the bottom right corner, there is successful liquid coming out of our condenser, so that means condensation. We're in the chilled stage, and we should be hopefully seeing something happen here shortly.
You should hear a call out for the next steps of propellant loading happening. Sorry, propellant condensing happening soon.
Right. Yeah, and it's not actually... we're actually venting, hopefully at this point, liquid. And it's actually instantly evaporating?
Vaporizing, yeah.
That's the right word. Not sublimating because it's not a solid. But it's instantly
Vaporizing.
just vaporizing into the gaseous form, and that's why you see so much gas coming out of such a short system. I believe you can even tell which vent line is coming out because that's the one that is frozen.
Yeah, so you can see at this point that things are getting properly chilly, and every line that is exposed to liquid nitrogen is very cold at this point.
Yeah. You can tell if something is being touched by liquid nitrogen just by if it's got snow covered in it. And after the operation, the crystals on this, because they're formed over such a slow period of time, especially on low humidity days, massive crystals form, and it's one of the best things you can take a photograph of. Obviously, this is not something we can do right now, but during our cold flows, it's a great time. Especially with all inert gases, I would like to clarify. So, when we're, can you kind of talk about why we decided to go with a pressure system instead of maybe a autogenous recovery or turbo pumps or just something of that nature?
Yeah, so similar to what we did with our ignition system, one of the main reasons we went with a pressure-fed system is that it is a very simple way of making a liquid rocket. It's very simple and it's very cheap. It really cuts down development time. Pumps are very difficult to design and operate. It would require a huge testing and validation campaign. And really, kind of our aim here is to get the minimum viable product that can accomplish the mission, which we can do with a pressure-fed system.
Right. And minimum viable product is, it's still an understatement, but compared to the most complicated rocket we could do, absolutely. That's what we're focusing on. That's why our tanks aren't COPVs, except for our helium tank, due to pressure requirements. But that's why we're looking at it.
COPV in this case standing for a composite overwrap pressure vessel.
Yes.
Another great question in the chat, why is a needle valve being used for venting nitrogen instead of a pneumatic valve? So, the needle valve is being used in this case because it allows for very precise control of flow rate into the jacket, which is necessary because it is a very precise operating point that we need to keep the methane condensing at.
Right. And if you think about it overall, this, I believe the abrupt changes you're hearing is actually a pneumatic valve that the operator has found is convenient to use, so that's why he uses it. But the needle valve provides us with a baseline, so we only have to do small adjustments with kind of a bang-bang-esque system, but just manual, of a pneumatic valve. And what this is doing is it's sealing off our vent lines so that we can have a exact known pressure, and as of course, due to thermodynamic properties, pressure controls the temperature because the temperature is controlled by the boil-off point of the liquid. And as the liquid boils off, it'll build pressure if we have a closed valve. So it's kind of a feedback loop that we need to be constantly balancing. One of the things that we are having happen now is stuff is starting to get really cold. Actually, sure. Why not use closed loop control for the condenser?
Well, this is another example of we had to adapt quickly to a new set of challenges. We originally did not plan to use a liquid methane condensing system. However, due to supply chain related issues, we had decided to move from a directly acquiring liquid methane to condensing it ourselves using gaseous bottles. And because we had to put this system together in a small amount of time, I think from formulation to build, it was only, I think, 3 or 4 weeks.
Yeah.
Before we did a cold flow with the system. We didn't have time to write a closed loop controller and verify it and put it through the steps. To be honest, a human being is way simpler for this kind of application.
Right, and especially because this is on an entirely separate DAC, we're able to have a person solely dedicated to working on this singular issue, and that's really important. If our main operator was also having to do all of this at the side, it wouldn't be feasible, and you're right, we would have to use closed loop control. But because we have 2 operators, we're able to dedicate one to this and make sure nothing goes south. Again, we are just waiting for the overall chilling of the condenser. The colder it gets, the more precisely we know the temperature of the overall condenser. And also, as ice builds up on the outside, that lowers the thermal transfer. And what that allows us to do is better really understand and keep the temperature at a known value. So, when we are firing, let's talk about the heat deflector, or the flame diverter. What do we expect it to do?
So the aim of the flame diverter is to make sure that the plume of the engine does not obliterate the concrete beneath it. And so, this basically steel plate is subjected to, frankly, crazy thermal and, gas impingement loads on it. So one thing we do to reduce that wear on the system is we flow water over the flame deflector. And so this will cool it down and make it so that we don't essentially obliterate our nice steel flame deflector.
Right, and it's, there is still some wear on the flame deflector after each operation. However, it is significantly less than we would expect without a flame deflector, and it also allows us to control which way the flame goes. This high-velocity air can wreak havoc on everything and throw pebbles everywhere, so by sweeping the ground beforehand, and really making sure everything is nice and clean, we try to minimize the risk of flying debris to our camera equipment and farther out.
That's right, and our flying debris could also even damage the engine.
Yeah.
Which would be a really unfortunate event.
Yes. Flying debris is the enemy in this case, almost as bad as foreign objects in any of the lines.
Yeah, and for those just joining our stream, we have done purges on the system prior to loading our...
Hey guys, we're looking pretty full on our end. I think we're going to go proceed to a doer swap. Over.
So you just heard a call out for a doer swap.
But why do we swap a doer?
Can I have confirmation someone's wearing cryo PPE?
Definitely is putting on the cryo PPE. Over.
So,
Copy all.
we perform a doer swap to make sure that we have adequate liquid nitrogen levels going into propellant load. This just makes us more confident in our ability to perform the test when we have a full load of liquid nitrogen available to the system before we do our hot fire.
Right, and it's one of those great things about working at Zucro is we have a bulk supply of liquid nitrogen, so we're able to have this extra, really safety blanket that helps us.
In chat, answering a couple questions. First up, how secure are the cameras?
So, the cameras are varying levels of securedness, I guess. On the
Definitely
left
is
wall,
on cryo PPE. Over.
at the middle of the left wall on your screen right now, you can see...
Copy all. Okay, go ahead and close MV-LN202.
You can see a camera that is bolted to the wall. In the middle bottom right now, you can actually see our 4K camera, which is capable of, which is where you get some of the nice photos. When we use it, we don't actually have access to it today, but
MV-LN202 is the gas valve. Over.
behind the mirror,
202 is closed. Over.
Copy. Go ahead and unload MRN203.
back left behind a mirror is actually where we would keep a high-speed camera, and that's maybe where you saw some of the great shots we got out of Hotfire 1. All other cameras are secured by really heavy weights. Most of the time they're lead bricks or sometimes steel plates.
MRN203 is unloaded. Over.
Moving on to the next question.
Copy. Disconnect QD from MV-LN202, the gas valve.
We utilize a solid propellant ignition system. Essentially, a bit of solid propellant on a stick that we put up into the engine combustion chamber.
Right. And obviously we
The
can't...
QD is disconnected. Over.
Unfortunately, this is still...
Copy, go ahead and open MV-LN202, the gas valve, to vent the dewar.
Unfortunately, this is still a competition, so we can't give away all of our secrets. But needless to say, it's a relatively simple system that we feel is not only robust, but is something that we can repeat every time we make it.
And then the next...
MV-LN202 is open.
Our
Copy, go ahead and close MV-LN201, the liquid valve.
Our propellant tanks are made of aluminum 6061.
I go ahead and wait a little until most of the venting's over.
And is most of our lower and
Copy.
upper frame. The tanks are welded.
Actually, let's go ahead and close LN201.
And the tank outer walls are also the airframe airframes.
We just closed
Yeah.
MV-LN201.
Yeah, you're all good. I'm sorry, we had someone interrupting.
And yes, just as a clarification, we will not have high-speed footage from this test.
It is very sad, but we were generously loaned that high-speed camera, and it is currently with the original research group that is using it. So
We
they
need
had
to
a break
open MV-LN201, the liquid valve.
that happened to line up with Hotfire 1, so we were able to get some incredible footage out of it.
MV-LN201 is open. Over.
We will still have high-resolution pictures and video available, though.
Yep, we have a DSLR that is auto-triggered by our control system, as well as a 4K camera that will be constantly recording as soon as people leave the courtyard. So, we are partially through this dewar swap now. Just to reiterate, why do we do a dewar swap?
We do a dewar swap to make sure that we have adequate liquid nitrogen levels going into propellant load, and so that people do not have to be on the courtyard for the safety critical parts of the test.
Right. And as you may have noticed, we are just dumping liquid nitrogen out. So this first dewar is entirely dedicated to just chilling the overall system.
Yes, and chilling is probably the longest part of the system going into propellant load at this point. So once chilling happens, and all of our
The
methods...
dewar is pretty close to ambient right now. Over.
We will quickly head into propellant
Yeah,
load.
copy, yeah. Now that we're vented, let's go ahead and close MV-LN201, the liquid valve.
And following propellant load, we will proceed
MV-LN201 is closed. Over.
immediately
Copy,
into
go ahead and
load.
remove fittings from MV-LN201, the liquid valve.
So, we have a question in chat. Are we using a COT COPV for a pressure intake? So that has a few
Yeah,
questions.
remove the flex line from the ground support equipment.
Do you want to go over the definition of COTS,
Copy.
COPV, and then talk about what we did for our pressure tank?
Yeah, so COTS, or commercial off-the-shelf, stands for essentially a technology you can purchase directly from a vendor and integrate into your system. And COPV stands for composite overwrap pressure vessel. Think scuba tanks, or lightweight scuba tanks, or firefighter air tanks, which I believe is what our COPV is.
Yes.
If I'm not wrong.
Well, so it's actually a funny story. We had some very particular requirements for our COPV that's not met, but we were able to find a large, well-known supplier of COPVs that was doing a run of tanks that just happened to fit near enough our specifications that we could accept the difference for a significantly higher volume customer. So we were able to pay a significant price, but we were in exchange we were able to have the tank made without having to buy it entirely ourselves and design it entirely ourselves. However, yes, COPVs are something that we are looking forward in the team in the future. It's a long way in the future, and it turns out the problems are tough.
Yeah, so we do have a design team at this point working on a custom filament winder for the team, and that's a capability we really plan to leverage in the future going into our next vehicles.
Right. It's not something we were able to take advantage of for the system, but again, we had a massive recruiting class this year, and one of the things we try to do is incorporate as many of the new team members into technical roles as soon as possible, and by putting them on teams that are developing things that we actually need and we don't have the ability to do right now, we believe is the best way to do that. Do we want to... So, an interesting topic is our chamber and nozzle. Is it ablative? Is it a regenerative? What is it?
Yeah, so our
The
engine...
reflexos is disconnected. Over.
Our engine thrust
Copy,
chamber
all. Go ahead
assembly.
and close MV-LN202, the gas valve.
is a carbon overwrapped silica phenolic ablative engine. So that may sound complicated. Let me break it down for you. So our engine uses what is called an ablative cooling cycle.
MVL202 is closed.
That means that
Remove and replace the LN2 doer.
the engine cools itself by physically burning away part of the chamber
Be wary of the cables on the ground.
as the
Over.
propellants burn within it.
Copy, we'll make sure we don't trip on anything. Over.
This does limit the life of the engine, but it dramatically simplifies the design of the engine and allows the team to really iterate fast and get this rocket through the design cycle. And it also, in our case, allows it to be very light. It doesn't have to be made of metal. So what we have done for this project is directly overwrap the ablative material, the silica phenolic, with a carbon fiber overwrap.
Yeah.
And then we integrate this TCA, thrust chamber assembly, up onto the injector.
Right.
It is not the same thing as a Dragon heat shield. I'm not exactly sure the chemical formulation of what they use, but silica phenolic is very different.
And one quick thing: if you are a new rocket team and you're like, we want to do regenerative cooling, we recommend contacting us. We have contact info on our website. We have many thoughts about what may or may not be right for your first team, and we want to make sure that other new teams get started.
If your engine is in place, we're going to reconnect the flex hose. Over.
Why is it wrapped in carbon
Copy,
fiber?
go ahead.
Wrapping our TCA in carbon fiber dramatically reduces weight of that component, and it's really just one of the ways that we can exploit a mass advantage on our system.
Mass is one of those things that we have to optimize for at every stage. That's why everything's aluminum 6061. That's why we have a lot of different pressure sensors that are getting taken on for testing, off for flight. That sort of stuff is what we're really doing.
Next question in chat. Yes, we do model the changing thrust from changing throat area for our sims. And we also model changing thrust based on tank pressure.
Yes.
And we integrate this directly into our simulations so that we get an accurate altitude prediction for the
The
flight.
door is reconnected. Over.
I do not believe we have enough time in the screen
Copy,
to
can you
go
confirm you connected the QD to MD LN202, the gas valve?
That is correct. Over.
to go into the exact details of why regen
Copy,
is
can
hard.
you also
Do you want
move
to give a
the
high
door
level
back a
overview?
little? It's blocking one of the cameras.
Yeah, so it's kind of a synthesis of a bunch of different elements in our design space that makes regen not really worth it for our application. Number one, an impulse limit.
Yeah, we're moving the door that we just swapped out. Does it look better now? Over.
Sorry, restricts the amount of
No,
time
we
you
were
can get out
referring
of
to
an
the
engine
wheel
for a certain
door.
pressure.
It's blocking the vent cams.
And it would also likely drive us away from a pressure-fed
Can we just
system
move the camera?
because of the large pressure losses associated with flowing through a regenerative chamber.
Yeah, we just want to be able to see those vents. That does sound easier, so you can go ahead and move it.
And as Carter is
Alright, we'll move some stuff around. Let us know if it looks okay.
As Carter is saying in chat, regen engines with a pressure-fed engine would require very large tank pressures, and large tank pressures drive up wall thickness. Wall thickness would drive up total mass.
And if you increase total mass, you need higher tank pressures.
Yes.
It's a really vicious cycle, and why we try to stay on the bottom of it this entire time. You did just hear a call out. Looks like one of our cameras are getting moved, so it'll take a while for us to go back to that view.
Alright, does that look okay? Over.
Perfect. Over. Now, if the door is completely connected, go ahead and load MR-N203 to 100 PSI on PG N205. Correction, let's go ahead and just fully increase the regulator. Over.
In
I
addition,
think we talked over each other, but MR-N203 is loaded to 100 PSI. Over.
in addition to the previous reasons we've stated,
Actually, could you load MR-N203? Could you fully increase it? Over.
previous reasons we've stated for not going with a
It's fully
regenerative
increased.
engine.
Over.
This is our second
Awesome. Go ahead and open MV LN202, the gas valve,
this is
and
our
verify RV N201 is not venting.
second iteration of Boomie Zoomie, and we really wanted to take
Gas valve
advantage
is
of the
open
design
and we're
heritage
not
we've had.
venting. Over.
Copy. Open MV LN201, the liquid valve.
Liquid valve is open, and we are flowing liquid. Over.
Nice. Flowing liquid is what we want to hear in this situation. You see, we have a slightly different camera here, which means we can't see some of the chilly stuff happening with the flex line, but you can better see the vent line. Hopefully here we will, maybe depending on the fog, we will see what's happening. For the lifetime burn duration on your blade of, 10 seconds.
10 seconds design. We think we can maybe hold out for longer, but that's what it's rated to. That's what we've designed it to. And we
Alright, we have completed our dewar swap. We are going to go back and resume with nominal procedures.
Nice.
We are going to begin lock system preload.
Let's go.
Nice. So now we're moving into preload, and this is kind of an important step for us, a really critical step. After we move into propellant load, things will start happening really fast, so you should be listening to our comms and making sure that you
Can you verify
ready for the
that
fire.
MV OXO1, the liquid valve, is closed, and MV OXO2, the gas valve, is closed?
Both oxygen dewar valves are closed. Over.
So, what happens if we ablate too much? Is it just performance, or does everything go boom?
Well, in the event that we ablate more than we think, this is actually a familiar problem to us. This was another outcome of the BZ1 hot fires that was not exactly predicted, was the ablation rate was much higher than expected. And I believe that was because the injector
Can you open the
configuration...
dewar pressure build valve and raise the dewar pressure to 100 psi?
The injector configuration we used was a fuel-centered pintle injector, which meant that our very hot
Copy,
and
the dewar pressure
reactive
is currently
liquid
at 50,
oxygen
and we are opening the pressure field circuit.
was
Over.
burning the ablative much more than we predicted.
Awesome. Go ahead and give confirmation when the dewar pressure reaches 100 psi. Over.
On BZB, we elected to switch this and go for a LOX-centered pintle, which should hopefully mitigate this issue. But if we do ablate too much, it will just degrade performance.
Yes.
The dewar pressure is at 70 right now. Over.
The ablative is not providing any structural component, or meaningful structural component.
Copy.
That is all provided to us by the overwrap that you saw with the carbon fiber.
So yes, we would just lose thrust because the throat area gets larger,
Yeah?
and our engine performance would degrade.
And that's, of course, one of the things we're trying to test with this. Of course, it is no longer Halloween, but the mist of nitrogen is flowing over us. You can see we've dumped a
Dewar
good
is
amount of
at
nitrogen.
75 psi.
For operations like this, we wish they were indoor, just from a temperature perspective. But in this environment, what are some of the dangers you can have with indoor operations with gaseous stuff?
Yeah, so not even with an indoor operation, but in any kind of enclosed space, there is a danger presented by having non-oxygen inert gases close to operators. So we're very mindful of that and need to make sure that our operators are actually intaking oxygen and to make sure they are not suffocating.
Yeah, that we always like our operators at the end of the day to come back with a nice, clean bill of health, and we do a lot of things, whether it be our PPE, whether it be our communications, to ensure that is the case.
Yep.
And as we're moving on to the propellant loads, you're going to hear something about pressure build circuit. What is that? What does it do, and what's the effect on the overall rocket?
The dewar is at 80 psi. Over.
So when we run
Copy.
the pressure build circuit, that allows us to build our pressure in the dewars, and that allows us to fill at either a lower or higher pressure on the actual rocket.
Yeah.
And we have a minimum acceptable pressure that we can fill the rocket at, if I am correct.
Yeah, and one of the things we can do is actually, that pressure is what we're using to push all of the liquid from the low place that is our dewars up into the rocket. So without that, we wouldn't be able to do anything.
The dewar is about 90 psi. Over.
Awesome. They're getting callouts now for the pressure in the dewars, so that's
Copy.
always good to hear. Seems like operations are going nominally at this point, which is always great to hear. We're getting some of that ice, and as you can see, perhaps up close in the right-hand camera shot, dead center, you can actually see some of the long-form icicles that cause when you're having something cold and have that very low humidity. They're forming nice icicles on it that are able to really grow into much larger than you'd see in any other environment. The next thing we should talk about is why that random tube is coiled. So if you see right under one of our valves, there is a coiled tube. What happens when you coil a tube, and what's the purpose of it?
So when you coil a tube, you basically put a large amount of length between that and whatever's behind it. And so that results in some things. It results in a fully developed flow, and it also kind of isolates it from what's upstream in the system.
Right.
The door's at 100 psi. Over.
And I believe in this specific case,
Copy all.
it is
Let's
for.
go ahead and move on. Go ahead and open MV Aux 01, the liquid valve.
I believe in this specific case, it is for making sure a cryogenic fluid is actually is a gas before it hits that specific valve. So we aren't really going to declare our set pressures, unfortunately.
MV Aux 01 is open. Over.
Anyone that knows rocket design calcs can figure out a lot of stuff from that, so we are quite ready to
We're moving on to helium system
say it.
preload.
If you can find it on our website, then you're good.
Copy.
And we're expecting an ETA, I'd say
Okay, courtyard, make sure you're all wearing
hour, but if I
safety
knew for sure,
glasses.
I'd be lying. Do you have any idea?
I think it's under an hour at this point. We are approaching.
Copy. Everyone is wearing safety glasses. Over.
We are approaching
Courtyard, verify MV HE01 is closed.
the fast-moving phase of our operation.
MV HE01 is closed. Over.
Once we move into propellant,
Courtyard, open MV
expect
HE02.
hot fire very soon.
And during propellant loading and vehicle pressurization, we will only be providing light commentary as needed. We will instead choose to let you listen to the sounds of the rocket as it comes alive and fires, as well as the control room and everyone else just kind of celebrating. So, in terms of what happens after we fire the rocket, how do we clean up from this? How do we depressurize the system? How do we make sure it's safe?
Yeah, so safing the system is a really huge component of running our operations. So the first thing we do is, depending on whether it's an abort,
MV HE02, the helium bottle is open. Over.
whether it's an abort or
Copy,
a
go ahead and
nominal
open
finish,
MV HE03, the other helium bottle. Over.
we have a different set of procedures that we run to make sure that the system is in a safe state. So safe in this context means propellant is offloaded from the vehicle, either by boiling off or by venting.
Yep.
It means that we don't have any pressure in the system,
Yeah.
and that operators are safe to approach the vehicle.
Right. Yep, that's really what we're looking for in a safe system, is it to be just that. And what happens if everything goes dark? Do we have a switch we can just flip to make everything safe?
Yeah, we have two, I believe, pickle switches.
Yes.
As their aptly name, and these pickle switches allow us to put the system into a completely safe state.
Yeah. It's an amazing thing. It's the pickle switches.
Both helium bottles are open. Over.
Copy, verified PG HE01 reads over 4,950 PSI.
We are only reading 4,400 psi on PG HE01. Over.
Sounds like we had an off nominal helium system reading, so we'll see what that means. The operators are more than prepared to deal with this. Everyone in our op room.
Can you confirm that MV HE02 and MV HE03 are all the way open? Those should be 6K bottles. Over.
They're well known.
Yeah, we're supposed to be 6K bottles. They're both all the way open, and the gauge still reads 4,400 psi. Over.
That, of course, does not sound like a good time, but that's what we have to do. Contingency.
We're going to go ahead and load just so we can verify that it might be a gauge problem. So go ahead and load.
So this is just. What's the difference between preloading
Okay, we're
system
going
and
to
loading?
continue. Load MR HE02
setting
to
regulation
4,950 PSI or whatever you can get it to. Over.
Yeah, so basically what we're doing at this point, the procedures with people out near the rocket, is getting the BCLS in the state it needs to be
Alright, can you let us know what read on
autonomously
your
load
VT as we're
propellants.
opening it? Over.
So everything we're doing at this point is on the BCLS, or ground system side. Everything involving actually filling the rocket with propellants happens when people have retreated behind safe cover.
Right. And one of the important things to note here really is when we're doing all of this, the human safety factor is the most important to us. So once we go out there,
We're reading 4,310.
barring
We believe that's all we're going to
extremely
get. Over.
unlikely circumstances, none that
Copy,
I can
both our
think
gauges
of,
are
but
about 4,300. Over.
barring effectively, as an insurance would call an act of God, there will not be anyone in the courtyard with a vehicle pressurized and with propellant.
Copy all. We're going to move forward with preload for preparations. Clear all foreign objects from the test area. Courtyard. Over.
We're getting very close now.
Yes, we're fully in preload mode right now. This is the last step that happens before propellant load. Just as a warning and reminder, we will really lighten up on the commentary.
We have foreign objects in the vicinity of the test area. Over.
So what's your favorite thing to watch?
Go ahead and verify all cameras are recording and that the DSLR and everything is set up.
That's the camera call out.
Yeah.
Pretty soon after this, people will retreat behind solid cover. Now, to answer your question, Aiden, I think the most interesting thing when we're watching loading is definitely seeing the tanks fill sequentially and the levels increase. You can see just by the ice building up on the outside.
Oh, yeah, it's incredible.
Copy all.
Yeah.
Go ahead and open the water deluge supply valve. Over.
That is the water we're talking about. That helps make sure our flame trench doesn't burn ourselves. For those asking for an ETA, we unfortunately don't really know, but it should be coming here before, hopefully on the current trajectory before the end of the hour.
Yeah, I fully expect us to fire within the end of the hour at this point.
Yes.
Water valve is open. Over.
Knocking on some wood.
We are moving quickly through the preload procedures.
Copy. Verify open lock steward pressure build circuit.
Once we are in loading mode, things will start to move very quickly. We will give some very brief updates.
Build circuit is open. Over.
But after we move into auto sequence, things are going to move very fast.
MRN201 is loaded to 300 psi. Over.
And you can also see how much the velocity has
MRN201 is 300 psi. Over.
Exit of our LN2 doer.
Copy. Verify the courtyard gates are chained. Over.
Chaining? What's chaining?
Say again?
Chaining. When we chain up a gate, what does that mean?
Yes. So when we chain together two different gauges in the system.
Put up chains.
Oh, yeah, sorry.
You're good.
Chaining the courtyard. This is a safety procedure to make sure that
courtyard gates are chained. Over.
Does not accidentally enter our test area while we are
Copy. You might hear release valve by possibility, but don't worry about it. Go ahead and knock on the knock block for good luck.
What is a knock block?
Rocket engineers are very superstitious.
Copy.
And we find it very necessary to knock on wood before any kind of major procedure, or when we say any kind of statement that would indicate the effectiveness of our vehicle.
That is true. There's a reason why we named our system the way it was. Black Cat launch system is named for all the good luck.
We also just left the courtyard.
Absolutely.
Over.
So,
Copy. And all the test cells and roof are cleared and chains have been installed and the blast doors are closed, correct?
we are now on to propellant load. So
Safety just
what does that
verified
really
we are
mean?
good, so you're good to retreat to the control room.
Propellant load is a very critical part of our procedure. At this point,
Alright, let's go check rocket tail. Declan's coming back. Over.
We are going to start filling the vehicle with liquid methane and liquid oxygen. This is the last step before we fire the rocket. Sorry, the second to last step before we fire the rocket. The last step before we fire the rocket is loading helium into our helium
Can I
tank.
have someone go ahead and close the back cell really quick? Over.
Then we will begin our auto sequence.
Close
Once
the
the
garage
auto
door.
sequence is started, there are
Correct.
three options: abort
Okay, I'll do that.
automatically, abort manually, or a successful hot fire.
Yes, and I think with the fog slowly rolling in, it's time for us to sign it off. We will be doing light commentary as we see fit, just marking out any specific callouts. But overall, this will be the end of our commentary. It's been great having you. My name's Aiden Powers.
I'm Jack Costello.
And we hope you enjoy this upcoming hot fire.
Alright, the back shell garage door is closed. I'm closing the blast door and putting the chains. Over.
Copy.
Alright, we're going to return back to the courtyard. Over.
Giving control room. Over.
Copy.
So we got a quick question about what all that venting is. That is the excess LN2 from our cryo jacket that we use in order to condense methane. And as you can of course see, we are now into lock system loading, and the LOX tank is chilling in. As you can now see, the fuel system loading has begun, which means the bottom tank should begin filling in. In case you are wondering what the excessive amount of smoke is in the courtyard, that's actually liquid nitrogen. It seems likely that we had a slight overpressure in our system, so we're just trying to bring it down.
A little more, and then we will be moving on to vehicle pressurization. Over.
Just to reiterate it, because I believe we missed the first part of that announcement, we are completed with vehicle load. We're just waiting a little bit longer for the chill-in, and then we will be moving on to vehicle pressurization. We are in vehicle pressurization.
Vented propeller load, we are going to pressurize the vehicle.
Everything's going to start happening real quick here.
We are pressurizing the vehicle. We're waiting until it's steady.
We are on the final section. Fire.
Hello, we are on Section 6, Fire, for the test operation. We are starting to log our high-speed data. We have loaded Hotfire auto sequence. We are arming our auto sequence. We are running auto. 3, 2, 1.
That is a successful test.
You guys just heard a successful test.
We have completed a successful, I believe, full duration test of Boomie Zoomie B.
You can see it's rather toasty, and we will be getting more data as the night goes on, but we would like to thank you for...
Successfully tested!
As you can tell, our control room is ecstatic. We are here, quite frankly, and it's amazing. All of us have spent so long working on this project together, and we want to thank all that made it possible. It's really been a great journey to get here. Yeah.
2 years in the making, our first successful full hot fire.
The system shut down after that very exciting fire.
You can hear the call out. We are going into system shutdown.
Yep, this is the end. We can't stop now. You can see we have a toasty flame diverter by the end of it. It's going to be quite...
We're going to open the water.
to perhaps make something a little less toasty. But overall, it's been a great test. We couldn't have asked for anything better. We'll be moving on to data reduction, and from everyone in the media team, from everyone on PSP Liquids, I thank you for joining us tonight in this great moment.
Thank you so much for joining us. I am Jack Costello.
And I'm Aiden Powers. We're signing off for the night. Thank you very much.
Thank you so much for joining.